What if everything you see, touch, and experience the vastness of the cosmos, the depth of an ocean, even the warmth of sunlight on your skin, wasn't truly three-dimensional at all? What if, at the most fundamental level, our entire reality is nothing more than an incredibly detailed hologram, projected from a two-dimensional surface we can't even perceive? This isn't science fiction. It's a radical theory shaking the foundations of physics, known as the holographic principle. And if it's true, it means the universe as we know it is a cosmic illusion, a shadow of something far stranger happening at the edges of existence. Think about your favorite movie. No matter how lifelike the images appear, they're just light projected onto a flat screen. Now, imagine that same concept applied to reality itself. The holographic principle suggests that all the information needed to construct our three-dimensional world, every star, every atom, even your thoughts, might actually be encoded on a distant two-dimensional boundary. It's as if the universe is a movie and we're the characters who have forgotten we're living inside the projection. This idea didn't come from a wild guess. It emerged from the deepest puzzles in black hole physics, where scientists discovered something astonishing. The information swallowed by a black hole doesn't vanish. Instead, it's somehow preserved on its surface like a cosmic hard drive. That revelation led to an even bigger question. Could the same be true for the entire universe? Today, we're diving into one of the most mind-bending ideas in modern science. We'll explore the evidence that's making physicists question the very nature of reality, from quantum experiments that hint at hidden dimensions to mathematical models that suggest space itself might be an emergent illusion. By the end of this journey, you'll see the world, and maybe even yourself, in a completely new light. Because if the holographic principle is correct, it doesn't just change our understanding of the cosmos. It redefines what it means to exist. So, are you ready to peel back the layers of reality and discover what might lie beneath? Let's begin. To grasp the holographic principle, picture standing in a room surrounded by mirrors. Every angle reflects a slightly different version of you, yet all those images originate from a single source, your physical body. Now, stretch that idea to the scale of the universe. Physicists Leonard Susskind and Gerard T. Hooft proposed something equally counterintuitive. The three-dimensional reality we perceive galaxies, planets, even our own bodies, might be nothing more than a projection. But here's the twist. The source code for this cosmic illusion isn't stored in the world around us. It's etched onto a distant, two-dimensional surface, like information burned onto the surface of a DVD. This idea didn't emerge from pure speculation. It was born out of a paradox involving black holes, those gravitational monsters that devour everything, even light. When matter falls into a black hole, classical physics says it's gone forever. But quantum mechanics insists information can't just disappear. Susskind and T. Hooft found a stunning resolution. The information isn't lost inside the black hole. Instead, it's smeared across its event horizon, the point of no return, like a message written in invisible ink on the edge of space-time. If that's true for black holes, could it apply to the entire universe? The holographic principle dares to say yes. Think of it like a video game. The lush forests, sprawling cities, and intricate characters you see on screen aren't real in a physical sense. They're generated by lines of code, a flat, two-dimensional set of instructions. In the same way, our universe's richness might emerge from a hidden layer of data we can't see. This flips classical physics on its head. Newton and Einstein described a world where space and time are fundamental, the stage upon which everything plays out. But the holographic principle suggests space itself is an illusion, a byproduct of information interacting on that distant two-dimensional surface. It's as if the stage isn't real, the actors are just shadows dancing on a wall. Skeptics might dismiss this as philosophy, but the math tells a different story. string theorists have shown that equations describing a three-dimensional universe can be perfectly mirrored by equations operating in two dimensions. It's like discovering the same story written in two completely different languages, with neither version missing a single detail. Experiments with quantum entanglement, where particles instantly influence each other across vast distances, hint at hidden connections that align eerily well with holographic predictions. The implications are staggering. If the universe is a hologram, then free will, consciousness, even the passage of time might be emergent phenomena, side effects of a deeper, simpler reality. It's a humbling thought. Everything we are, everything we experience, could be the universe's way of reading its own hidden script. Black holes aren't just cosmic vacuum cleaners. They're the key to unraveling one of the most profound mysteries in physics. The story begins in the 1970s when a young physicist named Jacob Bekenstein made a startling observation. He realized black holes have entropy, a measure of disorder usually tied to the chaotic motion of particles. But here's the catch: entropy depends on volume. The more space something takes up, the more ways its particles can jumble around. Black holes, though, don't play by those rules. Their entropy isn't linked to their volume. Instead, it's tied to their surface area, specifically the area of their event horizon, the point where gravity becomes so strong even light can't escape. This was bizarre. It suggested something fundamental about black holes, and by extension, the universe wasn't what we thought. Entropy isn't about what's inside a black hole. It's about the information stamped onto its boundary like a cosmic fingerprint. Then came Stephen Hawking, who took this idea even further. He showed black holes aren't completely black. They emit radiation, now called Hawking radiation, slowly leaking energy, shrinking over time, and eventually vanishing. But this created a paradox. If a black hole evaporates, what happens to all the information it swallowed? Quantum mechanics says information can't be destroyed, yet Hawking's math suggested it was vanishing into nothingness. That's where the holographic principle offered a solution. If the entropy of a black hole is proportional to its surface area, not its volume, maybe all the information it ever consumed is still there, encoded on its event horizon like a celestial hard drive. Imagine throwing a book into a fire. The pages burn, but if every word, every letter was somehow etched into the flame's glow, the information wouldn't be lost. It would just exist in a different form. That's the essence of the holographic principle. The three-dimensional book, our universe, might just be a projection of information stored on a two-dimensional surface. This revelation reshaped how physicists see reality. The Bekenstein-Hawking formula didn't just solve a black hole puzzle. It hinted that space itself might be secondary, a kind of illusion emerging from a deeper, flatter layer of reality. Think of a painter creating the illusion of depth on a flat canvas. The universe could be doing the same thing, tricking us into experiencing three dimensions when the real work is happening on a hidden, two-dimensional plane. Experiments with quantum gravity and string theory have since backed this up. The math shows a striking equivalence. The equations governing particles in three-dimensional space can be rewritten as interactions on a two-dimensional surface without losing a single detail. It's like discovering the same symphony can be played perfectly on a grand piano or a humble flute. The notes are different, but the music is identical. That's the power of the holographic principle. It doesn't just suggest our universe is a projection. It gives us the tools to decode the hidden script. String theory takes the holographic principle from a fascinating idea to a concrete mathematical framework, bridging the gap between gravity and quantum mechanics in a way that still leaves physicists in awe. At the heart of this connection is something called the AD/CFT correspondence, a mouthful, but a game-changer. It stands for anti-de Sitter space and conformal field theory, and it's the closest thing we have to a Rosetta Stone for decoding the holographic universe. Imagine you're trying to translate a poem from an ancient language, but instead of words, it's written in the fabric of spacetime itself. That's what string theorists like Juan Maldeisner accomplished when they discovered that a theory of gravity operating in five-dimensional space, anti-de Sitter space, could be perfectly described by a quantum field theory living on its four-dimensional boundary. It's like finding out a symphony and a ballet tell the exact same story, just through completely different mediums. This discovery didn't just support the holographic principle, it gave it teeth. In this strange mathematical duality, the equations governing the behavior of particles in the lower dimensional quantum world can be rewritten as the equations of gravity in a higher dimensional space, and vice versa. No information is lost, no details are blurred. It's a perfect mirroring of physics across dimensions. Think of it like a video game engine rendering a sprawling 3D world. The engine itself runs on flat, two-dimensional code, but the output is a fully immersive environment with depth, texture, and motion. The AD/CFT correspondence suggests our universe might operate the same way, with the messy, quantum interactions happening on a distant boundary, generating the smooth, gravitational reality we perceive. This connection solves one of physics' biggest headaches, uniting Einstein's theory of gravity with the quantum world. Gravity, as we know it, doesn't play nice with quantum mechanics. But in this holographic framework, gravity isn't a fundamental force, it's an emergent phenomenon, a side effect of quantum information interacting on that lower dimensional surface. It's the difference between thinking of waves as independent entities and realizing they're just the ocean's way of moving. Skeptics might wonder how much of this is real science versus mathematical elegance. But the predictions hold up. Black hole thermodynamics, quantum entanglement, even the behavior of exotic materials in labs, all align eerily well with holographic models. Experiments with ultra-cold atoms and superconductors have even found patterns that mirror what the AD/CFT math predicts, as if nature itself is leaving breadcrumbs pointing back to a two-dimensional source. The most mind-bending part, if this is true, then the fabric of reality isn't just stranger than we imagine, it's stranger than we can imagine. The universe isn't a thing. It's a process, a dynamic projection of information playing out on an unseen surface. And if string theory and the AD/CFT correspondence are right, we're not just passive observers. We're part of the code. Quantum entanglement, the spooky connection between particles that Einstein famously dismissed, might be the secret glue holding our holographic universe together. Picture two coins, each spinning randomly, yet no matter how far apart they are, they always land on the same side at the same moment. That's the bizarre reality of entangled particles. But here's where it gets wild. This phenomenon doesn't just link particles, it might stitch spacetime itself into existence. The ER=EPR conjecture, proposed by physicists Leonard Susskind and Juan Maldeisner, bridges two seemingly unrelated ideas, entanglement and wormholes. Einstein and Rosen, in the equation theorized that tiny tunnels called Einstein-Rosen bridges could connect distant points in space. Meanwhile, EPR refers to the entanglement paradox Einstein, Podolsky, and Rosen highlighted. Susskind and Maldeisner's bold insight, these aren't separate phenomena. Entanglement might literally create microscopic wormholes, weaving the fabric of spacetime like threads in a cosmic tapestry. Think of it like a puppet show. The puppets on stage, stars, planets, even you, appear to move independently, but their motions are secretly controlled by strings. In this analogy, quantum entanglement is the hidden network of strings. The more particles are entangled, the more complex the illusion of a three-dimensional world becomes. Experiments with entangled particles have shown something astonishing. Measuring one instantly affects its partner, even if they're light years apart. This action at a distance defies classical physics, but if spacetime itself emerges from entanglement, it starts to make sense. The particles aren't communicating faster than light. they're fundamentally linked through a deeper geometric structure we can't see. Lab tests are putting this idea to the proof. Researchers studying holographic quantum systems have found that entangled particles behave as if they're connected by tiny bridges in spacetime, just as ER equals EPR predicts. In one experiment, physicists simulated a black hole's event horizon using ultra-cold atoms. When they entangled particles on opposite sides of this artificial boundary, the system mimics the geometry of a wormhole. It's as if entanglement is sketching the blueprint for spacetime itself, one quantum connection at a time. This flips how we think about reality. Space isn't just empty nothingness, it's a dynamic web of quantum relationships. Time might not flow like a river. It could emerge from the way entangled particles update their shared information. Even gravity, the force that sculpts galaxies, might just be entanglement's shadow. The more we probe these connections, the clearer it becomes. The universe isn't built on matter and energy alone. It's built on relationships, tiny, invisible handshakes between particles that collectively dream up the world we perceive. What if the universe around us, the smooth curves of planets, the ripple of gravity waves, even the flow of time itself wasn't perfectly continuous, but instead stitched together from unimaginably tiny building blocks? At the smallest scales imaginable, far beyond what any microscope can see, spacetime might not be a seamless fabric. It could be pixelated, a cosmic mosaic where each pixel is a unit of reality so small, it makes atoms look like giant boulders in comparison. This is the world of Planck-scale physics, where the holographic principle takes on a startlingly concrete form. The Planck length, named after physicist Max Planck, is the smallest meaningful measurement in existence, roughly 1 trillion times tinier than a hydrogen atom. At this scale, the smooth geometry of spacetime predicted by Einstein's equations begins to fray. Quantum mechanics suggests space isn't infinitely divisible. It's grainy, like a digital photo zoomed in until you see the individual pixels. But here's where it gets even stranger. If the holographic principle is correct, these fundamental pixels of reality aren't scattered through three-dimensional space. They're arranged on a two-dimensional surface like dots on a vast cosmic screen. The 3D world we experience, just an incredibly convincing projection. Researchers at Fermilab took this idea from theory to experiment with a device called the holometer, a laser-powered marvel designed to detect spacetime's hidden graininess. Picture throwing a pebble into a perfectly still pond. The ripples that form will be smooth and regular unless the water itself is made of invisible, jittery particles too small to see. The holometer works similarly, firing laser beams down two perpendicular paths and measuring whether they wobble as they bounce back. If spacetime is pixelated at the Planck scale, those laser beams should pick up minuscule fluctuations, a faint fuzziness betraying reality's underlying digital nature. While the holometer hasn't yet found definitive proof, its existence marks a turning point. For the first time, we're not just theorizing about the holographic universe. We're trying to touch it. Other experiments, like gravitational wave detectors, are also hunting for Planck-scale anomalies. Every time two black holes collide or neutron stars spiral into each other, the resulting ripples in spacetime might carry hidden clues, subtle fingerprints of pixelation encoded in the gravitational waves. Think of it like watching an old film reel at the cinema. When the projector runs smoothly, you see fluid motion, but slow it down enough and you'll notice the individual frames. If the holographic principle holds, our universe has its own version of those frames, Planck-sized bits of spacetime flickering into existence moment by moment. And just as the movie's illusion relies on the real being flat, our 3D reality might depend on information arranged in two dimensions. The implications rewrite the rules of existence. Matter, energy, even causality could emerge from interactions between these pixels. Time might not flow like a river but click forward like frames in a cosmic flipbook. And if space-time is pixelated, then black holes, those cosmic shredders of information, might simply be places where the universe's resolution maxes out, their event horizons acting like the edge of a digital screen where the pixels stop. Critics argue we're centuries away from detecting Planck-scale effects directly, but the holographic principle offers a breathtaking loophole. If reality is a projection, we might not need to probe those unimaginably tiny scales. The answers could be hiding in plain sight, written in the quantum entanglement of particles or the way black holes encode information. Every experiment nudging us closer to that revelation isn't just testing physics, it's testing whether we're living inside the universe's most spellbinding illusion. Buried within the faint glow of the cosmic microwave background, the oldest light in the universe lies a potential clue that could shatter our perception of reality. This afterglow of the Big Bang, a whisper of radiation from over 13.8 billion years ago, isn't just a relic of the past. It might be a cosmic cipher hiding evidence that the universe is a hologram. Scientists have scoured this ancient light for irregularities, hunting for anomalies that don't fit the standard model of cosmology. What if the odd patterns they've found aren't just statistical flukes? What if they're fingerprints of a two-dimensional code imprinted on the fabric of spacetime itself? One of the most tantalizing hints comes from something called anomalous power asymmetry. When researchers mapped the cosmic microwave background, they expected it to look roughly the same in all directions, a uniform tapestry of tiny temperature fluctuations. Instead, they found a bizarre lopsidedness. One half of the sky shows more variation than the other, as if the universe's blueprint had a smudged edge. Traditional physics struggles to explain this, but the holographic principle offers a provocative possibility. If our three-dimensional universe is projected from a two-dimensional boundary, those inconsistencies could be artifacts, glitches in the translation from flat code to volumetric reality. Think of it like a vinyl record. The music isn't stored in the grooves as sound, it's encoded as tiny physical bumps. Only when the needle reads them do the vibrations emerge as symphonies. Similarly, the CMB's anomalies might be the needle skips, revealing the universe's hidden grooves. Another puzzle lies in the large-scale alignment of temperature fluctuations. Some patterns in the CMB appear improbably synchronized across vast distances, as if parts of the early universe were mysteriously linked. This eerily mirrors what the holographic principle predicts: quantum entanglement on a cosmic scale, where distant regions are secretly stitched together by information on a shared two-dimensional surface. Imagine two people on opposite sides of the world holding identical snow globes. When one shakes theirs, the other's moves in sync, not because of some signal between them, but because both are projections of a single underlying design. Cutting-edge telescopes like the Planck satellite have sharpened our view of these anomalies, but the data remains tantalizingly ambiguous. Some theorists argue the statistical significance isn't strong enough to overturn cosmology yet. Others, like physicist Craig Hogan, propose more radical experiments. His team once searched for holographic noise in gravitational wave detectors, theorizing that if spacetime is pixelated at the Planck scale, it should produce a faint jitter in the fabric of reality itself. While the results weren't conclusive, the pursuit continues. Future observatories, like the European Space Agency's upcoming Lightbird mission, will analyze the CMB with unprecedented precision, potentially spotting patterns that today's tools can't resolve. Critics dismiss these ideas as speculative, but history teaches us that revolutions often begin with anomalies. The cosmic microwave background once seemed like mere noise until it revealed the Big Bang's echo. Now it might be whispering something even stranger, that the universe isn't just expanding, it's unfolding line by line from a hidden script written in two dimensions. Every flicker in that ancient light could be a stroke of the pen, a reminder that what we call reality might be the most elaborate projection of all. Gravity has always been the silent architect of the cosmos, bending starlight, sculpting galaxies, and keeping our feet firmly planted on Earth. But what if this force isn't what we think it is? What if gravity, like the warmth of sunlight or the pressure of wind, isn't fundamental at all, just an illusion emerging from something far stranger? The holographic principle flips our understanding upside down, suggesting gravity might be a side effect of quantum interactions playing out on a hidden two-dimensional surface. Think of temperature. When you feel the heat of a fire, you're not sensing some innate property of hotness. You're experiencing the collective frenzy of countless atoms jostling at breakneck speeds. Temperature doesn't exist at the level of a single atom. It's a large-scale phenomenon born from microscopic chaos. Gravity, according to the holographic principle, could be just like that, a cosmic mirage created by the frenetic activity of quantum bits on a distant, flat boundary. This idea traces back to entropy, the universe's tendency toward disorder. Just as the heat of a gas emerges from the unpredictable motion of its molecules, gravity might emerge from the way information is shuffled and shared on that two-dimensional surface. Black holes offer a clue. Their immense gravitational pull isn't just about mass, it's tied to the information stamped on their event horizons. The more data packed onto that surface, the stronger the gravity we perceive in 3 dimensions. It's as if the universe is running a calculation, and gravity is the output, a force generated by the invisible math happening behind the scenes. String theory takes this further with the AD/CFT correspondence, showing how equations governing gravity in a higher dimensional space can be perfectly mirrored by quantum interactions on a lower dimensional boundary. Picture a concert hall where the music you hear isn't produced by instruments on stage but by vibrations in the walls themselves. The melodies, harmonies, and rhythms, everything you experience, are just echoes of a deeper, hidden performance. Experiments are beginning to test this radical vision. Quantum simulators designed to mimic holographic systems have shown that entangled particles can exhibit behaviors eerily reminiscent of gravitational effects. It's like watching ripples form in a pond and realizing they're not caused by thrown stones, but by something scribbling on the water's surface from below. Even spacetime's smooth geometry might be a trick of the light, a statistical average of countless quantum interactions, the way a bustling city seen from a distance appears as a serene skyline. Critics argue gravity's elegance in Einstein's equations makes it hard to dismiss as emergent. But then again, no one in the 18th century imagined heat was anything more than an invisible fluid. Today, we know better. If the holographic principle holds, future generations might look back at our era and smile at the quaint idea that gravity was ever considered fundamental. The force that shapes the cosmos could be nothing more than a shadow, a reflection of the universe's hidden, flatter truth. Both the holographic principle and simulation theory suggest reality might not be what it seems, but that's where the similarities end. Simulation theory, popularized by figures like Elon Musk, proposes we're living inside an advanced computer program created by some hyper-intelligent civilization. It's a gripping sci-fi concept, but it hinges on an unproven assumption that reality requires a programmer. The holographic principle, on the other hand, isn't about artificial creation. It's a rigorous mathematical framework emerging from black hole physics and quantum gravity, suggesting the universe naturally encodes itself on a lower dimensional boundary. Think of the difference between a painting and the laws of perspective. Simulation theory wonders if an artist painted our world, while holography reveals the canvas might fundamentally work in 2 dimensions no artist required. One key distinction lies in their scientific credibility. Simulation theory is philosophical speculation, fun to debate but impossible to test with current tools. The holographic principle, though radical, is rooted in equations that predict real phenomena, from black hole entropy to quantum entanglement. It's like comparing alchemy to chemistry. Both question the nature of matter, but only one offers testable reactions in a lab. When physicists say the universe might be holographic, they're not pointing to a machine running the simulation. They're describing a structural quirk of spacetime itself, as inherent to reality as waves are to the ocean. Another difference: intent. Simulation theory implies purpose. Some entity built this world for a reason, even if we don't know it. Holography strips away that narrative. If our universe is a projection, it's not for anyone's benefit. It's just how physics works, like how sunlight doesn't choose to cast shadows. This makes holography more elegant to scientists because it doesn't rely on unprovable layers of designers or code. The universe could simply operate this way because the math demands it, the same way ice forms hexagonal crystals without a blueprint. The two ideas also diverge in how they handle information. Simulation theory treats reality like data in a supercomputer, with pixels that might glitch if the system lags. Holography describes information as invariant, preserved on a cosmic boundary no matter how it's projected. Imagine watching a movie on an old projector versus a digital screen. The first might jam or distort, revealing its mechanical nature. The second ensures the film's essence stays intact, whether you're seeing it in 3D or as a flat image. Holography suggests our universe is like that digital film. Its source code is indestructible, written into the fabric of physics itself. Critics of both ideas often lump them together as fringe fantasies, but holography has a resilient simulation theory lacks. When researchers found black holes obey thermodynamic laws, or that quantum particles mirror equations from string theory, they weren't testing for programmers. They were uncovering patterns that point to a deeper, possibly lower dimensional logic. That's why Nobel laureates like Gerard T. Hooft take holography seriously. It's not about who built the universe, it's about how the universe builds itself. So while simulation theory asks, are we someone's experiment? The holographic principle asks something far stranger. What if reality is just physics' way of solving a problem we're only beginning to grasp? One is a story about creators, the other is a revelation about creation, with no storyteller needed. Neuroscience might hold an unexpected key to understanding the holographic universe, and it all begins with how your brain stores memories. In the 1960s, psychologist Carl Pribram made a startling discovery. No matter which part of a rat's brain he removed, the animal could still recall complex tasks, as if memories weren't stored in any single location but distributed across the entire brain. This flew in the face of conventional wisdom, which assumed memories had fixed addresses like files in a cabinet. Pribram's research pointed to something far stranger. The brain might function like a hologram where every fragment contains the whole. This idea mirrors the holographic principle in physics. Just as a universe's worth of information could be encoded on a two-dimensional surface, a single shard of a holographic film can reconstruct the entire image it captured, blurrier but complete. Your brain, according to Pribram, might work the same way. Memories, sensations, even consciousness itself could be patterns of interference waves, overlapping and interacting to create the rich, three-dimensional experience of being. It's as if your mind isn't just perceiving reality, it's built from the same holographic blueprint as the cosmos. The implications are dizzying. If both the brain and the universe operate holographically, could consciousness be more than a passive observer? Some theorists, like physicist David Bohm, propose that the mind doesn't just process reality, it participates in its unfolding. In Bohm's implicate order, the universe is a dynamic hologram where every part influences the whole, and perception itself might collapse possibilities into tangible experience. Think of a sculptor shaping clay. The clay exists independently, but its form emerges through interaction. Similarly, consciousness might not create reality, but it could be the chisel that gives it definition. Experiments in quantum cognition add weight to this notion. Studies show that human decision-making often follows quantum probabilities rather than classical logic, as if our thoughts are entangled, capable of holding conflicting states until the moment of choice. This doesn't prove the brain is quantum, but it hints at a deep structural resonance between how we think and how the universe operates. Even optical illusions, where the brain fills in missing visual data, echo the holographic principle's core idea. Perception constructs dimensionality from incomplete information. Skeptics argue these parallels are metaphorical, not mechanistic, yet the math reveals eerie similarities. The equations describing neural networks, how neurons fire in cascading waves, resemble those governing quantum fields and holographic entropy. It's like finding the same equation scrawled in two different notebooks, one labeled cosmology and the other neuroscience. Whether this is coincidence or clue remains hotly debated, but the overlap is too tantalizing to ignore. If the holographic principle is right, then consciousness might not be locked inside our skulls. It could be a localized expression of a deeper, universal process, a flicker of the cosmos recognizing itself. After all, if the universe encodes information holographically and the brain processes information holographically, perhaps the line between thinker and thought, observer and observed, isn't a wall at all. It's a mirror. Fermilab's holometer isn't your average science experiment. It's a laser-powered detective, hunting for something that shouldn't exist if our textbook understanding of space-time is correct. Tiny, Planck-scale jitters that would betray the universe's hidden pixelated nature. Picture two laser beams traveling down identical paths, perfectly synchronized like identical twins dancing in unison. In a perfectly smooth, continuous space-time, they'd stay locked in step forever. But if reality has a fundamental graininess, if space itself is made of discrete, jittery bits at the quantum level, those lasers would gradually fall out of sync, revealing fluctuations smaller than an atom over a mile-long distance. That's the holographic noise the holometer was built to catch. The device itself is a marvel of precision. Twin 40-meter vacuum tubes house lasers bouncing between mirrors, protected from every conceivable earthly vibration, passing trucks, distant earthquakes, even the subtle expansion of the pipes as sunlight warms them. The team at Fermilab had to account for noise 1,000,000 times larger than the signal they sought, like trying to hear a whisper in a hurricane. When they ran the experiment from 2014 to 2015, the results were ambiguous. The holometer detected fluctuations, but were they evidence of holographic space-time, or just some stubborn earthly interference they hadn't eliminated? The data couldn't confirm either way, leaving physicists in a tantalizing limbo. Critics argued the null results proved nothing, while holographic enthusiasts pointed out the experiment was pushing against the very limits of measurement technology. Think of it like Galileo's first telescope, barely powerful enough to spot Jupiter's moons, but hinting at celestial truths far beyond its initial grasp. The holometer team knew their instrument was just the prototype. Future versions with longer baselines or space-based designs free of Earth's vibrations might yet catch spacetime's quantum fuzz in the act. What makes this pursuit so revolutionary isn't just the technical challenge. It's the philosophical stakes. Most physics experiments study phenomena within space-time. The holometer was attempting to study space-time itself, probing whether it's a fundamental entity or an emergent illusion. It's the difference between studying water ripples and questioning whether water exists. Even the experiment's failure advanced the field, forcing theorists to refine their predictions about how holographic noise should manifest. Some now suggest the signal might be frequency-dependent, like tuning a radio to catch a specific station. Others propose looking for correlated noise patterns across multiple detectors worldwide, eliminating local artifacts. The holometer's legacy lives on in next-generation experiments. Gravitational wave observatories like LIGO, initially designed to catch colliding black holes, are now being scrutinized for unexplained low-frequency noise that might align with holographic models. Meanwhile, tabletop quantum gravity experiments using supercooled atoms are testing whether entangled particles behave as if they're connected through microscopic wormholes, another holographic prediction. The holometer might not have delivered a smoking gun, but it proved something equally important, that the wildest ideas in theoretical physics aren't beyond the reach of experiment. Reality's deepest secrets could be hiding in plain sight, encoded in the faintest tremors of the quantum void. Black holes, the universe's most enigmatic monsters, hide a paradox at their edges so explosive it threatens to rewrite physics. It's called the firewall paradox, and it pits Einstein's general relativity against quantum mechanics in a battle that could only be resolved by the holographic principle. Picture this: you're falling toward a black hole's event horizon, that invisible threshold where gravity becomes inescapable. According to Einstein, you'd feel nothing special at first, just the serene pull of spacetime's curvature. But quantum mechanics tells a different story. The vacuum of space isn't empty, it's a seething foam of virtual particles popping in and out of existence. At the event horizon, these particles can separate, with one falling in and the other escaping as Hawking radiation. Here's where things get dicey. For information to be preserved, a quantum must. Those escaping particles must be entangled with the ones inside the black hole. But they must also be entangled with particles that left earlier, creating a monogamy problem. Quantum entanglement can't be shared infinitely, the only solution. A blistering wall of energy right at the horizon, a firewall that would incinerate anything crossing it. This firewall idea horrified physicists. It meant the event horizon wasn't just a quiet boundary, it was a cosmic kill switch, violating Einstein's principle that free-falling observers should experience nothing dramatic. Enter the holographic principle. If the universe encodes information holographically, then the real action isn't happening in the three-dimensional space around the black hole, it's unfolding on its two-dimensional surface. In this view, the firewall isn't a physical barrier, it's a mismatch in how we're interpreting quantum correlations. Think of it like a glitch in a virtual reality headset. The struggle isn't happening inside the black hole, it's in how information is being projected from the boundary. The holographic approach suggests entanglement works differently than we thought. Instead of particles inside and outside the black hole being directly linked, they're both tied to data on the event horizon itself, like two actors taking cues from the same script. This reshuffles the firewall paradox. There's no need for a violent rupture in spacetime because the real quantum connections lie on the horizon's surface, not in the volume. It's as if the universe outsourced its entanglement problem to a lower dimensional layer where the math stays consistent. Critics argue this is just clever wordplay, but the math holds up. String theorists have shown that in holographic models, firewalls either don't form or are artifacts of choosing the wrong coordinates, like mistaking a shadow for a solid object. Even Hawking, in his final papers, suggested black holes might have soft hair as subtle surface features that store information without cataclysmic drama. The holographic principle doesn't just dodge the firewall, it redefines the stage, showing how quantum mechanics and gravity might be different views of the same deeper structure. Experiments remain out of reach. We can't exactly poke a black hole to check, but the implications ripple outward. If firewalls are illusions, then spacetime itself might be far more flexible, even ephemeral, than we ever imagined. The holographic principle doesn't just solve a paradox, it hints that the fiercest clashes in physics aren't flaws in our theories, they're clues pointing to reality's hidden blueprints. And if a black hole's lethal edge can dissolve into a coding problem on a flat surface, what else might we be misunderstanding about the nature of existence? Quantum mechanics and gravity have been locked in a century-long standoff, each reigning supreme in their own domain but refusing to play by the same rules. Quantum mechanics thrives in the subatomic world, where particles pop in and out of existence and entanglement defies distance. Gravity, sculpted by Einstein into the curvature of spacetime, governs the cosmos on grand scales. Yet when these titans collide, like at the edge of a black hole, physics breaks down in a storm of contradictions. The holographic principle doesn't just offer a truce, it rewrites the rulebook entirely, suggesting these aren't two forces at odds but two languages describing the same truth. Take the black hole information paradox. For decades, physicists wrestled with a simple question. When a black hole evaporates via Hawking radiation, what happens to all the information it swallowed? Quantum mechanics insists information can't vanish, yet Hawking's calculations showed it seemingly did. The holographic principle cracks this puzzle wide open. If the black hole's interior is a projection of data encoded on its two-dimensional surface, then the information was never truly inside to begin with. It's like realizing a movie character's memories aren't stored in their fictional brain but on the hard drive running the simulation. The paradox dissolves because gravity and quantum mechanics aren't fighting. They're different perspectives on a deeper holographic reality. String theories add S/CFT correspondence gives this idea mathematical teeth. It shows how a quantum field theory operating on a boundary like the edge of a black hole can perfectly describe gravity in the bulk space it surrounds. Picture a symphony where the sheet music is flat ink on paper, yet when played, it creates a rich three-dimensional experience of sound. The holographic principle suggests spacetime is that symphony, an emergent performance orchestrated by quantum interactions on a flat cosmic score. This duality isn't just elegant, it's functional. It explains why black holes have entropy tied to surface area, not volume. Their true storage isn't in the abyss below, but on the event horizon's skin. Even more startling, holography redefines what gravity is. In this framework, gravity isn't a fundamental force but an entropic effect, a tendency for the universe to maximize disorder, like heat diffusing through a room. When you feel Earth's pull, you're not sensing some invisible field. You're experiencing the statistical tendency of information on the universe's boundary to arrange itself in the simplest way. It's the difference between thinking a magician pulls rabbits from a hat and realizing the hat was never empty to begin with, just folded in higher dimensions. Experiments are catching up to these radical ideas. Lab-based quantum simulators designed to mimic holographic systems have shown particles behaving as if they're governed by gravitational laws, even in setups where no gravity exists. It's like watching ripples in a fish tank suddenly trace the same patterns as ocean tides, hinting that both are expressions of a hidden, unifying rhythm. Meanwhile, observations of quantum entanglement in materials like graphene reveal correlations that eerily resemble spacetime's geometry, as if the universe's fabric is woven from quantum threads we're only now learning to see. Skeptics argue holography is a mathematical sleight of hand, a clever trick with no tangible proof. But history favors theories that dissolve paradoxes, from Newton's gravity unifying celestial and earthly motion to Maxwell's equations marrying electricity and magnetism. The holographic principle doesn't just patch over the cracks between quantum mechanics and gravity, it reveals they were never separate to begin with. The force that bends starlight and the spark that animates atoms might be two notes in a song the universe has been singing all along, its lyrics written in 2 dimensions but heard in 3. To grasp how a universe of 3 dimensions could emerge from a 2-dimensional surface, let's start with something familiar, a movie screen. When you watch a 3D film, the glasses trick your brain into perceiving depth, but every pixel of that illusion originates from flat, 2-dimensional data encoded on the projector's reel. The holographic principle suggests reality might operate similarly, except instead of a projector, the universe uses the language of higher dimensional mathematics to flatten itself into a code we're only beginning to decipher. At the heart of this idea is Juan Maldacén's groundbreaking work on the anti-de Sitter/conformal field theory correspondence, AD S/CFT for short. It sounds intimidating, but the core concept is surprisingly elegant. Imagine you're holding a globe and a world map. The globe represents a universe with gravity, bulky, three-dimensional, and warped by mass. The flat map, on the other hand, is a lower-dimensional blueprint where gravity doesn't exist, but every mountain, ocean, and city is meticulously recorded in a grid of symbols. Maldaisner showed that these two objects, despite seeming utterly different, can describe the same reality. The equations governing the 3D globe are mathematically equivalent to those operating on the 2D map. It's like discovering that a symphony and its sheet music aren't just related, they're interchangeable, with no loss of meaning. This duality hinges on something called a bulk boundary correspondence. In the holographic universe, the bulk is the spacious, gravity-filled world we experience, while the boundary is the flat surface where information is stored. Think of it like a bubble. The soap film's surface, thin and nearly weightless, contains all the information needed to reconstruct the bubble's volume. Stretch this idea to cosmic scales and you've got add S/CFT. The boundary encodes quantum fields like the flat map, while the bulk manifests as spacetime, the globe. What's revolutionary here isn't just the math, it's the implication that gravity isn't a standalone force. It's a shadow cast by quantum interactions happening on the edge of existence. To see how this plays out, consider quantum entanglement, the spooky link between particles that Einstein famously resisted. In Maldaisner's framework, when two particles are entangled in the 3D bulk, their connection is mirrored by a tangled web of correlations on the 2D boundary. It's as if the threads stitching spacetime together aren't material at all, but information processing on a cosmic hard drive. String theorists have taken this further, showing how black holes, those gravity-driven monsters, can be perfectly described as dense clusters of quantum data on their event horizons. The math doesn't just match, it reveals that a black hole's terrifying interior might be a projection of chaos unfolding on its surface. Skeptics often ask, if we're living in a hologram, why can't we perceive the pixels? The answer lies in the Planck-scale, where spacetime's graininess would be 1 trillion times finer than anything we can measure. But here's the twist. Holography suggests we don't need to probe those infinitesimal scales to test the theory. Just as a vinyl record's grooves hold music we hear at a completely different scale, the universe's pixels might reveal themselves in subtle patterns like the way entangled particles behave or how black holes emit radiation. Experiments are already hunting for these fingerprints, from quantum simulators to gravitational wave detectors. What makes this more than abstract math is its power to solve real paradoxes. The holographic principle doesn't just suggest the universe is a projection, it shows how that projection can reconcile quantum mechanics and gravity, two frameworks that have resisted unification for a century. It's the difference between trying to force two puzzle pieces together and realizing they're actually part of the same piece, viewed from different angles. Whether add S/CFT is the final word or just a stepping stone, it's reshaped how we see reality's scaffolding, not as an edifice of space and time, but as a dynamic tapestry woven from information itself. If the universe truly operates like a hologram, projecting our three-dimensional reality from a flat, two-dimensional surface, what does that mean for the everyday experiences we take for granted, like the steady tick of time or the weight of our decisions? Time, for instance, might not be the unshakable river we perceive. In a holographic framework, time could emerge from how information updates itself on that distant cosmic boundary, like frames in a movie reel. Each moment we experience would be a snapshot, a slice of the universe recalculating itself. This could explain why time feels fluid, slowing down in moments of fear or speeding up when we're engrossed. If time isn't fundamental but stitched together from quantum interactions, even déjà vu might not be a glitch in our memory. It could be a fleeting glimpse of the universe's source code, a momentary overlap in the projection where information repeats before shifting to the next frame. Free will enters murkier territory. If every event stems from data processing on a two-dimensional plane, are our choices truly ours or just the universe playing out its predetermined script? But here's the twist: holography doesn't necessarily spell doom for free will. Instead, it might redefine it. Think of a chess game where the pieces follow strict rules, yet infinite moves remain possible. Our decisions could be both constrained by the holographic rules and genuinely open-ended, like characters in a novel who surprise even their author. Quantum mechanics already hints at this. At the smallest scales, particles exist in superpositions until observed, suggesting reality waits for interaction to crystallize. If consciousness itself is part of the projection, our observations might not just witness reality, they could nudge it into being. Then there's the mystery of dreams. In a holographic universe where information isn't bound by spatial dimensions, dreams might be more than random neural firing. They could be the brain tapping into the universe's underlying code, weaving fragments of unprocessed data into surreal narratives. It's like a computer running background processes what we dismiss as fantasy might be the mind interfacing with the raw scaffolding of reality. Some researchers even speculate that near-death experiences, with their vivid tunnels of light, could be moments when the brain briefly accesses the boundary layer, glimpsing the projector behind the cosmos. The implications ripple into consciousness itself. If the brain operates holographically, storing memories not in fixed locations but in distributed patterns, it mirrors how the universe stores information non-locally, everywhere at once. This could explain telepathy like phenomena in twins or the eerie sense of being watched. When two minds pick up on the same quantum fluctuations in the holographic field, information might transfer without any physical signal. Even intuition, those gut feelings science struggles to explain, could be the subconscious detecting subtle patterns in the data stream we call reality. Critics argue these ideas venture into metaphysics, but the math nudges us closer than ever. If space-time is an illusion, then so are the barriers we assume: separate thought from matter, past from future, self from universe. The holographic principle doesn't just reshape cosmology, it blurs the line between physics and philosophy, inviting us to question whether the world we perceive is the world as it truly is. And if reality is more malleable than we thought, perhaps the greatest illusion isn't the universe's projection, it's our certainty that we've already figured it out. Not every physicist is ready to accept that reality might be a grand holographic projection. Among the loudest skeptics are proponents of loop quantum gravity, a rival theory that takes a radically different approach to unifying quantum mechanics and general relativity. Instead of reducing dimensions, loop quantum gravity proposes that spacetime itself is woven from tiny, indivisible loops. Think of it as the universe's fabric being stitched together by threads a billion trillion times smaller than an atom. These loops form a network, creating space through their connections, much like how individual pixels compose a digital image. The key difference: in loop quantum gravity, spacetime remains fundamentally three-dimensional. There's no higher dimensional boundary encoding reality, just an intricate, ever-evolving mesh of quantum relationships. Critics of the holographic principle also point to its experimental challenges. While the math behind ADS/CFT correspondence is elegant, the anti-de Sitter space it relies on is a simplified model, a universe with negative curvature that doesn't match our own. Our cosmos appears flat or slightly positively curved, raising questions about whether holography can scale beyond theoretical sandboxes. It's like designing a perfect blueprint for a fantastical skyscraper, only to realize real-world gravity and materials behave differently. Until researchers can adapt holographic models to our actual universe's geometry, some argue it remains a beautiful abstraction rather than a practical description of nature. Another hurdle is the sheer scale of the proposed holographic boundary. If our three-dimensional reality is encoded on a distant two-dimensional surface, where exactly is this surface? The holographic principle suggests it lies at the cosmological horizon, the edge of the observable universe, billions of light years away. But that creates a paradox. If the boundary is constantly expanding as the universe grows, how does it update the projection we experience locally? Imagine a movie where the film reel is racing away from the projector at the speed of light, yet the images on screen stay perfectly synchronized. The mechanics of such a system remain speculative at best. Even entanglement-based tests face scrutiny. While quantum experiments have found correlations matching holographic predictions, alternative explanations exist. Some researchers argue these phenomena could stem from conventional quantum field theory without invoking extra dimensions or holographic encoding. It's the difference between attributing a magician's trick to unseen wires versus accepting that the illusion might rely on sleight of hand alone. Without a smoking gun, a measurement that only holography can explain the theory remains one compelling option among many. Then there's the philosophical resistance. The idea that space-time isn't fundamental clashes with centuries of scientific intuition. Einstein's relativity treats space-time as a dynamic actor, bending and warping under mass and energy. Demoting it to a secondary effect can feel like dismissing the stage while insisting the play must go on. As physicist Lee Smolin quipped, "You can't derive the existence of time from a theory that assumes time doesn't exist." For holography to gain wider acceptance, it must reconcile with the visceral reality of temporal flow and spatial depth that define human experience. Yet holographic theorists aren't without rebuttals. They argue that loop quantum gravity, while mathematically rigorous, struggles to explain cosmic phenomena like black hole entropy, precisely where holography shines. As for the AD-S/CFT mismatch, researchers are actively developing DS/CFT models de Sitter/conformal field theory to better fit our expanding universe. And while locating the holographic boundary seems abstract, supporters note that quantum mechanics once seemed equally untestable until technology caught up. The hunt for holographic noise in gravitational wave detectors or quantum simulators could shift the balance from speculation to evidence. What's striking isn't the conflict between these theories, but what they share. Whether space-time is built from loops, pixels, or projected information, all agree that reality isn't as solid as it appears. The debate isn't about whether the universe has hidden layers. It's about how those layers stitch together the world we perceive. In that sense, even the criticisms underscore how far physics has come from the clockwork cosmos of Newton. The holographic principle may not be the final word, but it's undeniably rewritten the conversation. Long before physicists ever scribbled equations about a holographic universe, ancient thinkers were plumbing similar depths with nothing but intuition and observation. Take Plato's allegory of the cave, written over 2,000 years ago. He described prisoners chained in a dark cavern, mistaking shadows dancing on a wall for reality. When one escapes and sees the true world outside, he realizes the shadows were mere projections, a distorted echo of something richer and more real. It's a chilling parallel to the holographic principle, where our three-dimensional experience might be a flickering shadow cast by a deeper, flatter reality. Plato didn't have quantum mechanics or string theory, but his cave allegory captures the essence of holography, that what we perceive as solid and tangible could be an elaborate illusion. Eastern philosophies arrived at comparable insights through meditation rather than mathematics. Hindu texts like the Upanishads describe the universe as Maya, a grand illusion, a veil obscuring the true nature of existence. The concept of Indra's net from Buddhist tradition is even more striking. Picture an infinite web of pearls, each reflecting every other pearl perfectly, creating a cosmic hall of mirrors where every part contains the whole. This isn't just poetic imagery. It's a startling metaphor for how holography suggests information is distributed non-locally, with each fragment encoding the entirety of the system. When physicist David Bohm proposed his implicate order, arguing that reality is a folded-up projection of a deeper dimension, he drew direct inspiration from these ancient ideas. Even Western mystics like the Hermeticists, who whispered, "as above, so below," hinted at a universe built on nested, repeating patterns. A concept holography echoes when it suggests the large-scale structure of spacetime emerges from microscopic quantum interactions. Alchemists, too, sought a prima materia, a fundamental substance underlying all appearances, much like how the holographic principle reduces the universe's complexity to a flat, information-rich boundary. What's remarkable isn't just that these ideas align, it's how they align. Without telescopes or particle colliders, these thinkers grasped that reality might be less substantive than it seems. They sensed that space, time, and matter could be layers obscuring a more fundamental truth. Science, with its equations and experiments, is now catching up to what intuition once whispered. The holographic principle doesn't validate mysticism, but it does reveal something profound. When human curiosity probes deep enough, whether through philosophy or physics, it often circles back to the same unsettling question: what if the world we know is just the surface of something far stranger? The next generation of experiments could finally push the holographic principle from mind-bending theory into observable fact, and scientists are already building the tools to make it happen. Imagine upgrading Fermilab's holometer from a prototype to an astronomical scale instrument, with laser arms stretching not just 40 meters but kilometers across. At that scale, even the faintest spacetime jitters, those Planck-scale pixels hinting at reality's holographic nature, would stand out like footsteps in fresh snow. Teams in Europe and Japan are designing such detectors, using ultra-stable cryogenic vacuums and quantum-entangled light sources to filter out earthly noise. But the real breakthrough might come from leaving our planet altogether. NASA and ESA have drafted concepts for space-based holometers, where lasers could race between satellites millions of kilometers apart, free from atmospheric interference or tectonic vibrations. In the pristine silence of orbit, these instruments could detect fluctuations a billion times subtler than anything possible on Earth, like listening for a single raindrop in an ocean of static. What would smoking gun evidence actually look like? Physicists are hunting for two telltale signs. First, holographic noise. Unlike random quantum fluctuations, this would follow precise mathematical patterns predicted by string theory. A distinct buzz in spacetime's background radiation, as if the universe were humming its digital resolution. Second, anomalous entanglement. If particles separated by vast distances show correlations that defy classical physics but match holographic models, like synchronized dancers whose moves are choreographed not by signals but by a shared underlying code, it would suggest their connection runs deeper than spacetime itself. Some even speculate that colliding black holes might leave holographic fingerprints in gravitational waves, subtle imprints revealing how information scrambles on their surfaces during merger. But the most daring test might come from quantum computers. Researchers at Google and IBM are programming qubits to simulate holographic universes in miniature, watching how entangled states generate emergent spacetime in their data structures. If these digital universes obey the same equations as our own, if virtual black holes in the simulation exhibit Hawking radiation matching real astrophysical data, it would be eerily strong circumstantial evidence we're living in a cosmic analog. Yet skepticism remains. Critics argue that even if future experiments find anomalies, they could stem from unknown quantum gravity effects unrelated to holography. That's why theorists are refining their predictions, identifying signatures unique to holographic projection. One key test involves the universe's frame rate. Just as movies stutter if projected too slowly, holographic reality might exhibit minute delays in how information updates across large distances. Ultra-precise atomic clocks aboard future spacecraft could detect these lags, comparing timekeeping between satellites to spot discrepancies smaller than a trillionth of a second. Another approach studies cosmic voids, vast empty regions of space where holographic pixelation might warp starlight in telltale ways, like a funhouse mirror bending reflections at its edges. The stakes transcend academic debate. If holography is confirmed, it wouldn't just revolutionize physics, it would redefine technology. Mastering spacetime's code could unlock unthinkable applications, from quantum communication networks immune to hacking, since information would be non-locally stored, to energy harvesting from vacuum fluctuations. Some futurists even speculate about holographic engineering, manipulating reality's projection by rewriting its boundary data, though that remains firmly in science fiction. For now, what makes this search extraordinary isn't just the scale of ambition. It's the humility behind it. For centuries, science assumed reality was built from tangible, measurable stuff. The holographic principle dares us to consider that everything, every atom, every thought, every galaxy, might be nothing more than shadows dancing on the cosmic cave wall. And soon, we might finally have the tools to turn and face the light. The Matrix famously offered us a red pill, a chance to wake up from a simulated reality into the real world. But what if the truth is stranger than fiction? Hollywood loves to play with holographic ideas, bending them into flashy special effects and dystopian plots, yet real physics hints at something far more nuanced and in some ways more unsettling. Take the iconic bullet time scenes where Neo dodges projectiles in slow motion. While the movie frames this as hacking a computer program, the holographic principle suggests something eerily parallel. If spacetime is a projection, manipulating its parameters might not require code, just a deeper understanding of the underlying quantum data. The difference: the Matrix implies a programmer pulling the strings, while physics points to mathematical laws operating without any creator at all. Christopher Nolan's Interstellar edges closer to real science, especially with its depiction of a tesseract, a higher dimensional space where time becomes physical. The film's climax, where Cooper navigates his daughter's bookshelf across time, mirrors holographic concepts like AD/CFT. In the movie, gravity transcends dimensions, allowing Cooper to influence the past. In holographic physics, gravity isn't a force confined to our 3D world. It's a shadow of quantum interactions on a 2D boundary. Nolan consulted physicist Kip Thorne to ensure the black hole visuals were accurate, but the film's tesseract is where science fiction brushes against theoretical possibility. The holographic universe wouldn't need a tesseract to bend time. The mere act of information updating on the boundary could reshape causality itself. Then there's the holodeck from Star Trek, a room that generates immersive, seemingly solid environments from force fields and light. It's a fun notion, but holographic theory flips the script. Instead of technology creating illusions, reality itself might be the illusion. The holodeck pretends to be real, while the holographic principle suggests our reality might pretend to be three-dimensional, the most mind-bending part. Star Trek's holodeck glitches, characters freezing or objects flickering, find a weird echo in lab experiments hunting for Planck-scale pixelation. If spacetime has a resolution limit, glitches wouldn't just be plot devices, they'd be inevitable artifacts of the universe's source code. Where Hollywood consistently misses the mark is in scale. Films like Tron or Ready Player One imagine virtual worlds built by civilizations, implying a top-down design. The holographic principle, though, removes the architect. There's no need for a superintelligence to render our universe. The laws of physics might inherently encode reality as a projection, no programmer required. It's the difference between a painting which demands an artist and a snowflake whose symmetry emerges from natural laws. the most poignant overlap between fiction and reality lies in existential questions. When Neo questions the nature of his world or Cooper grieves time slipping through his fingers, they're articulating fears holography makes tangible. If our senses can't be trusted, what's left? But here's where science offers a twist fiction rarely explores. In a holographic universe, real isn't binary. The world isn't necessarily a simulation or a lie. It might just be a different kind of truth, one where the boundaries between dimensions, between observer and observed, aren't walls but woven threads. The Matrix asked us to choose between a blue pill and a red one. Physics suggests the pills might be holograms too, and the choice itself could be part of the projection. Consciousness might be the most baffling piece of the holographic puzzle. Quantum mechanics has long hinted that reality behaves differently when observed, particles existing as probability waves until measured, then snapping into definite states like a cosmic game of peek-a-boo. This observer effect suggests something startling, that awareness itself could play an active role in stitching together the fabric of reality. In a holographic universe where the world emerges from information on a boundary, consciousness might not just witness the projection, it could be the projector. Think of a virtual reality headset. The images you see aren't just pre-rendered, they respond to your gaze, rendering higher detail where you look. Now scale that up cosmically. If the universe is a hologram, your observations might function like focal points, collapsing quantum possibilities into tangible experience. This isn't mysticism, it's math. Quantum decoherence, the process by which probabilities become certainties, aligns eerily with how holographic models describe information translating from boundary to bulk. Every time you measure a particle's position or a photon's path, you're not passively recording data, you're participating in the universe's rendering pipeline. The implications ripple into neuroscience. Research on binocular rivalry, where the brain alternates between conflicting images shown to each eye, reveals that perception isn't a direct feed from the senses. It's a constructive process, like a cinematographer editing raw footage into a cohesive film. If the brain works holographically, weaving fragments into a seamless whole, could reality itself operate similarly? Physicist John Wheeler's participatory universe hypothesis takes this further, proposing that observers are needed to bring the universe into existence, like an audience giving meaning to a play by witnessing it. Critics argue this veers into idealism, but lab experiments add weight. Quantum-delayed choice experiments show particles retroactively, deciding their behavior based on future measurements, as if time itself is a flexible projection. In a holographic framework, this makes sense. If reality is code executing on a boundary, your present observation might update past states the way a programmer edits a save file. Even the placebo effect, where belief alone triggers physiological changes, hints that perception might tweak the rules of the simulation we call reality. The most radical twist: if consciousness is fundamental to the hologram, then the boundary between inner and outer worlds blurs. Your thoughts might not be sparks in the brain's wetware, but perturbations in the universe's underlying data field. Near-death experiences, where people report vivid visions despite no brain activity, could be brief disconnections from the projection, like a VR user momentarily glimpsing the headset's edges. Psychedelics, which dissolve the ego's grip, might temporarily mute the brain's rendering filters, exposing raw information flow from the boundary. This isn't to say we're God's dreaming worlds into being. The holographic principle frames consciousness as less a creator and more a collaborator, a lens focusing the universe's self-referential loop. Just as a movie needs light to be seen, reality might need observation to be rendered. The eerie beauty of this idea isn't just that we're living in a hologram. It's that the hologram might be living through us. Our brains are exquisitely tuned for navigating a world of solid objects, gravity, and three-dimensional space. But what happens when reality might be written in a language we weren't wired to read? Optical illusions offer a sobering glimpse into these limits. Take the famous checker shadow illusion, where two squares of identical gray appear radically different because our brain insists on interpreting them under imaginary light. It's a reminder that perception isn't a direct window to truth, it's a survival tool, honed to prioritize useful approximations over absolute reality. Now scale that up to cosmic dimensions. If the universe truly projects from a two-dimensional boundary, our neural circuitry, evolved to dodge predators and grasp tools, might be as mismatched for comprehending this deeper reality as a flatworm trying to fathom quantum physics. Neuroscience reveals just how deeply our 3D bias runs. When you reach for a cup, your brain doesn't compute equations about quarks or spacetime. It creates a shorthand model where objects have edges, weight, and permanence. Even our language betrays this constraint. We speak of empty space as if it's a void rather than, as quantum field theory suggests, a seething network of virtual particles. The holographic principle compounds this disconnect by proposing that what we call space is an emergent property, like the illusion of depth in a stereogram. To a brain steeped in volumetric thinking, accepting that solidity might be a high-resolution mirage is like trying to smell color. Our hardware lacks the ports for that download. Some theorists argue this cognitive barrier isn't insurmountable. After all, we've already learned to conceptualize invisible forces like electromagnetism through mathematical abstraction. But math itself might be part of the problem. Our geometry, Euclidean angles, and Newtonian trajectories emerged from observing a 3D world. Even non-Euclidean models used in relativity still treat dimensions as fundamental. The holographic framework demands something more radical, that we intuit reality not as a stage but as a shadow where the directions we call up, down, and across are secondary effects. It's akin to explaining Instagram to a medieval scribe. The core metaphor of sharing images translates, but the underlying infrastructure of servers and pixels would seem like sorcery. Yet evolution has granted us one loophole: plasticity. The same brain that misreads shadows as objects can, through tools and collective knowledge, transcend its biases. Centuries ago, we believed Earth was flat because it matched our local perception until sailors and mathematicians proved otherwise. Today, we grapple with quantum non-locality, accepting that particles can be entangled across galaxies despite our neural resistance to action at a distance. The holographic principle may simply be the next hurdle in this long race to outthink our instincts. The real test lies in translation. Just as a painter renders 3D scenes on 2D canvas using techniques like perspective, scientists are devising ways to visualize holographic concepts through analogies and interactive models. Virtual reality simulations that let users experience higher dimensions might retrain our intuition, much like pilots learn to trust instruments over vertigo. The paradox is poetic. To comprehend a flat reality, we may need to immerse ourselves in artificial dimensions using illusions to pierce the ultimate illusion. This isn't just academic navel-gazing. If holography is correct, our perceptual limits could be blinding us to technological frontiers. Imagine a future where engineers manipulate reality's source code directly, editing the boundary data as effortlessly as we tweak pixels in Photoshop. But to get there, we'll first need to outgrow the primal certainty that what we see and what we are is as solid as it feels. The universe might be whispering its secrets in a tongue we're only beginning to lisp. Time might feel like an unshakable river carrying us from past to future, but what if that's the ultimate illusion? The holographic principle suggests time isn't a fundamental flow but a side effect, emerging from how information updates on the universe's two-dimensional boundary. Picture a flipbook. Each page is static, yet when you flip through them, the illusion of motion emerges. In a holographic framework, time could work similarly, a series of nows stitched together by the universe recalculating itself frame by frame. This aligns with eternalism, the radical idea that past, present, and future all exist simultaneously, like frames in a film reel stacked eternally in a block universe. Einstein hinted at this when he wrote, "The distinction between past, present, and future is only a stubbornly persistent illusion. Dive deeper and things get even stranger." If time emerges holographically, then the flow we experience might be more about entanglement, how quantum states link across the boundary layer, than any intrinsic arrow. Think of a cosmic game of dominoes. Each falling piece represents an update in the boundary's information, creating the sensation of progression. This could explain why time slows near black holes or under extreme gravity. The system's processing speed lags under intense data density. Even déjà vu takes on a new light. It might not be a memory glitch, but a momentary overlap in the projection, like a film reel briefly skipping back a frame. The block universe model fits this elegantly. Imagine spacetime as a loaf of bread where each slice is a frozen moment. From a higher dimensional perspective, the entire loaf exists at once. Your birth, this video, the heat-death of the cosmos, all equally real. Our consciousness, however, moves through the slices like a projector's beam, mistaking sequential illumination for intrinsic flow. Holography adds a twist. The slices aren't just there, they're rendered dynamically by quantum interactions on the boundary. It's as if the universe is both the film and the projector, with time as the light passing through. This challenges our deepest intuitions. Free will seems to crumble if the future is already written in the block, yet holography offers a loophole. If reality is code executing choices in real time, your decisions could be both predetermined at the boundary and genuinely open in the projection, like a video game whose storyline is fixed but allows player agency within its rules. Even entropy, the engine of time's arrow, might not be driven by particles shuffling toward disorder, but by information becoming increasingly scrambled on the cosmic hard drive. Experiments with quantum gravity are probing these ideas. Some theorists predict that if time emerges holographically, ultra-precise atomic clocks placed at different gravitational potentials should detect subtle discrepancies, not just from relativity, but from the universe's clock speed varying with boundary conditions. Others suggest that entangled particles separated by vast distances might reveal time's granularity through correlated anomalies in their quantum states, like synchronized watches ticking imperfectly in unison. The implications ripple into philosophy. If time is a projection, then grief for the past or anxiety for the future are like movie characters mourning scenes already filmed or dreading the reel's end. Yet this doesn't negate meaning, it reframes it. A holographic universe isn't a static painting but an ongoing computation, where every moment is both inevitable and freshly rendered. You're not just watching the film, you're part of the light casting the shadows, a thread in the tapestry the universe weaves to perceive itself. If our universe is a holographic projection from a two-dimensional boundary, could there be other projections, alternate realities flickering alongside our own like images cast from the same film reel? This is where holography collides with multiverse theories in ways that stretch the imagination. Picture a multiplex cinema where a single strip of film feeds multiple projectors, each screening a slightly different version of the same story. The holographic principle raises the tantalizing possibility that other universes might not be separate bubbles in a cosmic foam, but parallel renderings from a shared source code, variations etched onto the same fundamental surface. String theory's landscape of possible universes, each with different physical constants, could find new footing in holography. Instead of imagining infinite bubbles floating in some higher dimensional space, these alternate realities might exist as distinct views of the same boundary layer. Think of a gemstone with countless facets. Each face reflects light differently, yet all are part of the same crystal. Similarly, quantum fluctuations on the holographic boundary could generate divergent cosmic histories like branches splitting from a tree's trunk. This reframes the multiverse not as a collection of disconnected worlds, but as a kaleidoscope of perspectives emerging from a single, deeper structure. Black holes hint at how this might work. Just as a single event horizon can encode multiple interior geometries like different resolutions of the same image, the cosmic boundary might host countless universe profiles. Quantum entanglement adds another layer. If particles in our universe are secretly linked to counterparts in others through Planck-scale threads, it could explain phenomena like dark energy as a gravitational echo from parallel projections. Some models even suggest that what we call the Big Bang might have been a data overflow, a boundary calculation so intense it spawned secondary projections, birthing sibling universes. Critics argue this ventures into untestable metaphysics, but subtle clues might lurk in the cosmic microwave background. Just as a glitch in a video file reveals its digital nature, anomalies in the CMB's polarization patterns could betray interference from neighboring projections. Future quantum gravity experiments might also hunt for crosstalk particles in our universe responding to entanglement partners in another, like radios picking up faint signals from distant stations. The implications rewrite our place in the cosmos. If alternate realities share our boundary, we're not isolated accidents but iterations of something deeper, like different performances of the same symphony, each with unique improvisations. Whether this vision holds or not, it underscores holography's power to reframe not just our universe but all possible ones. If the universe is a holographic projection, a shimmering illusion woven from data on some distant two-dimensional surface, what happens to the weight of our existence? Does the love between parents and children, the sting of grief, the awe of a sunset become less real if they're shadows cast by a deeper, flatter truth? Philosophers have grappled with these questions for centuries, but holography drags them from abstraction into urgent relevance. Consider the ancient Japanese art of kintsugi, where broken pottery is repaired with gold, transforming cracks into beauty. The bowl isn't less valuable because it's fragmented. Its fractures become part of its story. In a holographic universe, maybe the same applies to us. Our lives aren't diminished by being projections, they're redefined, their meaning emerging not from some inherent solidity, but from the intricate patterns we etch into the cosmos's code. This challenges fundamental assumptions about identity. If our brains are holographic processors constructing reality from quantum interference patterns, then the self might not be a stable entity but a dynamic process, a melody played on the universe's strings. Think of a river. You can't step into the same water twice, yet we call it the Mississippi from source to sea. Similarly, your consciousness could be a fleeting configuration of information, constantly rewritten on the boundary layer. That doesn't make your joy or curiosity any less vivid. It just means you're more verb than noun, a cosmic event rather than a static thing, yet existential vertigo lingers. If reality is a kind of computation, are our choices illusions? Here's where holography diverges from hard determinism. In a quantum system, probabilities exist until observation collapses them. Your decisions might not be predetermined but co-determined, shaped by the interplay between boundary data and your participation in observing it. Imagine a tree branching in a fractal garden. Each path exists as potential until you walk it, and your steps become part of the garden's design. This isn't free will as we once imagined it, but it's not puppetry either. It's something stranger, a dance where the universe leads, yet follows your rhythm. The ethical implications ripple outward. If all matter is fundamentally information, then harming others isn't just damaging stuff, it's corrupting data in the universe's grand archive. Indigenous cultures have long spoken of rocks, rivers, and trees as kin. Sensing our interconnectedness, science now echoes. Holography could give this intuition mathematical teeth, framing ecology as literal system maintenance. Polluting a river wouldn't just be irresponsible, it'd be like deleting lines from a shared codebase, destabilizing the projection for everyone. Perhaps the most radical shift is in how we value time. In a block universe where past and future eternally coexist, urgency dissolves, yet holography reintroduces dynamism. If reality is constantly recomputing itself, then each moment is a fresh rendering, making presence the ultimate act of co-creation. Medieval monks painstakingly copied manuscripts, knowing their work preserved wisdom for the future. In a holographic frame, every mindful action is akin to that scribing, an edit on the boundary layer that ripples through the cosmic story. The meaning of life might not hinge on permanence, but on the artistry with we contribute to the projection's next frame. The holographic principle isn't just a quirky idea, it's a seismic shift in how we understand reality itself. By suggesting that our three-dimensional world might be a projection from a two-dimensional boundary, it doesn't merely tweak the edges of physics, it rewrites the foundation. Imagine if, after centuries of mapping constellations, we discovered the stars were just pinpricks in a cosmic curtain, revealing light from a hidden source. That's the scale of revelation holography offers, a universe where space, time, and even gravity could be emergent phenomena, secondary to the real action happening on a distant, flat surface. This isn't just about black holes or quantum mechanics anymore. It's about redefining existence, turning the solid ground beneath our feet into something as fleeting as a shadow dancing on a cave wall. Yet for all its elegance, the holographic principle leaves burning questions unanswered. If our universe is a projection, what or who is the projector? The math points to a self-sustaining system, a cosmic feedback loop where information processes itself into reality. But how does consciousness fit in? Are we passive observers or active participants shaping the projection with every thought and measurement? And what about the boundary itself? Where exactly is this two-dimensional surface storing the universe's data? Some theorists place it at the edge of the observable cosmos, while others propose it's woven into the fabric of spacetime at the Planck scale. Without a definitive experiment to pinpoint it, these mysteries remain tantalizingly out of reach. The skeptics, of course, have their say. For all its beauty, holography still struggles to explain why our universe appears flat, rather than exhibiting the negative curvature predicted by anti-de Sitter space. Competing theories like loop quantum gravity argue that spacetime isn't a projection but a lattice of interconnected loops, a three-dimensional tapestry with no need for hidden dimensions. And then there's the practical challenge. How do you test a theory where the most critical evidence might lie beyond our technological grasp? Fermi's old question echoes here. If holography is true, where's the empirical proof? But revolutions in science rarely unfold neatly. Einstein's relativity faced similar skepticism until eclipses and atomic clocks confirmed its predictions. The holographic principle, with its ability to dissolve paradoxes from black holes to quantum entanglement, has already reshaped how physicists frame their questions. Maybe the answers aren't in the stars, but in the spaces between, the quantum threads stitching our reality together, one entangled connection at a time. So where does that leave us? In a universe more malleable, more mysterious, and more magnificent than we ever imagined. Whether the holographic principle ultimately holds or becomes a stepping stone to something deeper, it's reminded us that reality is far stranger than our senses suggest. The next time you gaze at the night sky, remember, those stars might not just be distant suns, they could be pixels in a cosmic projection, fragments of a hidden code waiting to be deciphered. And if that doesn't send a shiver down your spine, consider this: what other illusions might we be living inside? The universe, whether two-dimensional or three, hasn't run out of secrets yet. Our journey to unravel them has only